Yeah. So this is your mock test 8. Okay. And mock test 8, and this is part 2. So we have discussed a few questions. We are discussing the rest, trying to discuss the rest. Okay. So this one is problem number 6. Okay. Problem number 6. So here we have numbers from 1 to 144 written on the board. Okay. And so it's a kind of moves are being made. A game is being, just a moves are being made. So each move, okay, so each move is, we are going to just pick two numbers and replace them by their difference. Okay, pick two numbers and replace them by the difference. And obviously the number of numbers is decreasing by 1 at each move. Now the question is, so eventually you will see that there will only be one number written on the board. So the question really is, can that number be 43? In short, that's what the question is. Okay. So that's the first part. Yeah. So can the final number be 43? Yeah. This one, I suppose all of you have done. So then let me just say it, because I think all of you have done it correctly. Well, really, in this one, the strategy is to find an invariant, right? In short, you have to find an invariant, and the invariant is the parity of the sum of the numbers on the board. Yeah. So there is an invariance, and the invariance is the parity of sum of numbers on the board. Yeah, because it's as if we are looking at a plus b and other things, and we're replacing this plus by a minus. Okay, but the parity of a plus b and a minus b is the same, so the parity does not change. Okay, and initially, so s initial, so this is so that you guys can check that it's the correct reasoning, or if you find some differences, then you can tell me. But I've seen this and most of it is correct, I suppose. This, so what is the parity of the sum? Yeah, anyone? Huh? Even, right? So the volume is, yeah. Okay, so this is even, right? Whatever it is even. This is 0 mod 2. Okay, so if it's even, then eventually also it should be even. So that implies that S final, which is just the sum of that number itself, this is also even. Okay, so it cannot be 43. Impossible. So answer is no. That's very, very straightforward. Okay, this all of everybody knows standard question. So then I asked this question in the, so when we in some other class, can you get every even number? You cannot get every odd number. So invariance principle tells you what you cannot get. But along with the invariance principle, you'll see this part of the questions come up sometime. What is possible? Okay. So with that in mind, the question is the number 44? Can the final number be 44? And let's say that when we are taking the difference, let's assume for the moment, though it won't matter in the end, because we can get the right strategy. But yeah, so then let's not say that at all. Yeah. Can the final answer be 44? So is there a way you can do the subtraction and get 44 in the end? Is there a way to get 44? That is the same thing. So any guesses? Have you guys tried anything in this? Okay. So let's take small cases and see, right? Let's take small cases and see. Otherwise, you don't know. So let's take 1 to 4. Yeah. So in this, my question first is there a way to get 0? Okay, so I didn't exactly follow the order, but yeah, this is you can okay. So you have to do this will come after 2 steps, but yeah, they'll get 1 and then you subtract it and you get 0. So the answer is yes. Yeah, you can get 0. Can you get 2? That's right. Yeah, so you do 3 minus 2, and then you do 4 minus 1, and then you do this. See, it's possible to get 2. Is it possible to get 4? 1 plus 2. You can't do 1 plus 2. Anyone else? Come on. What about other people? Yeah, that's all. Yeah, you do 3 minus 2, and then you do 1, and then you do 4, and 1 minus 1, and then you get 4 minus 0. Right? So you see, all the even numbers are possible. Yeah. So what do we learn from here? All even numbers, um, in this case at least, yeah, all even numbers less than 4 are possible. Yeah. I'm not writing that. We all can now, we can't forget that. Yeah. So with that in mind, can we have an idea, or you guys want to take some time and try with some other number and see? Yeah, just try it. Just 1 minute. Well, so the guess should be that the answer is yes. Do you guys agree? Yeah. Have you tried other numbers? So you can take just take a similar number, right? One doesn't have, or maybe you could take the other one to n whose sum is 4. So for example, whose sum is even. For example, you can take 3 mod 4, right? 1, 2, 3, 4, 5, 6, 7. So here you can give a reasoning if all even numbers are possible or not. So obviously, yeah, is all are all even numbers possible? Just see. So the sum is even. Okay, good. What about 4? Someone tell me how to get 4. Yeah, so how do you get it? Tell me. Ah, so you're going 1 and okay. Okay, 6 and 6. Uh-huh. 3. Ah, nice. Okay. So the way you have done it, you have kind of avoided that 4. And yeah, got the 4 by avoiding the 4. Okay, so that's one strategy. Okay. But what would be 2 also is possible? Good. So you can similarly check that 0 is also possible. Okay. Good. But then how would you prove this kind of thing now? So there are two ways here. Okay. Either you use some kind of an induction reasoning, or you see some pattern in how you make it. So when I was discussing with the kids, they were actually able to make it. Okay. Some of them actually made the pattern and then they told me you do this in general and you can do. Okay. So there are two ways. Either you go by induction, which doesn't mean that you will not know how to make it. You can recursively make it. Or you can give explicit construction. No. That's why this question is nice. Okay. Okay. I mean, I made it, so I'm just saying like that, but no. There are many questions like this which have, if you check the harder ones, and they have constructive. Yeah. So algorithms is a topic, right? In I mean, meaning the algorithmic reasoning. So induction is easy. That's your homework. You guys can just try. Okay. You have to formulate what happens for the other type of numbers, and then you can do induction. Okay. So just think, induction will work. So you have to think something like this. Okay. For 3 mod 4 and 0 mod 4, all even numbers less than that or equal to that are possible. I mean, it won't be equal with 3 mod 4. And again, for 2 mod 4 and 1 mod 4, all odd numbers and so on as possible. And then you can use, for example, in 7, if I use the fact that if you go from 1 to 6, then all odd numbers are possible to get from using 1 and 6. Yeah, then uh, uh, 5 is possible. 5 is possible, so 7 minus 5, 2 is possible. 3 is possible, then 4 is possible. If 3 is possible from here, then 4 is possible. 1 is possible from here, so then 6 is possible. Now only for 0, I need to give an explicit reasoning. So do you see, right? So how do you get 0 explicitly from here? That should not be difficult. Or do you get, if you don't get, then also tell me. Because 0, it seems like using induction, it seems, no, so there's something wrong with the 0. So that may be, no. So that's the whole point. It might be required in general because when you're using induction, so when you're trying to prove something for 3 mod 4, and this is the point about induction, at all levels, this is used. Yeah. So yeah, so when you're using induction, you need to have the information for all types of smaller cases because then your larger case will reduce. Is it coming? Uh, huh. Huh. Exactly. Exactly. So that's what, yeah, because there will always be an even number of ones. So that's, as I was saying, that is explicit. So that's what I actually did when I was doing the construction like this. And then, so you see, it's done by induction, it is done. Okay. So there's no problem. So you see, this is not a difficult question, but you may have to formulate all the things nicely. and you have to have this energy. So I've seen this with the kids. They are much more aggressive while solving. Okay, they are much more active in taking examples. You guys have not written the examples, not tried for 4 or 5, or maybe you have tried, you have not written. If you don't write, then yeah, it's not good. Anyways, let's try to write it. But I'm just wondering, so let's see, yeah, if there is a much easier, so what we have is induction, which means we have a recursive way to play a recursive algorithm, right? You call the lower function for smaller numbers and do it. But is there a direct answer? So let me ask this question. So let's give a bigger number. Let me also just think. I'm just speaking. If I also think, then we can get some direct way. So let's say that I have, let's take a different number now. Because it says something different. If there is a direct formula for getting it, that's different from recursive one, right? So you have 1 to 12. How do you get 6? Without using recursive, or yeah, let's see. How do you get 6? You should be able to get 6. We all agree. How do you get it? Yes, sorry. There should be, and I think there is a direct way. And it's similar to someone that said it already, I think. Here. Okay, that is it coming that way? Then it's good. So it's 11. Let's see. Okay. Uh, yeah. Right. That's what. Yes, yeah. So something like that. And this one, Chandan, what you're saying, this is 5, and this is 4, and this is no, but this might also work. So 5, 4. So 11, 9, 5. I missed a 9. Yeah, so just forgive me. Just check. So that might also, but it seems like there is a problem. But it may work in 2, 3 steps. Yeah, I can feel that. Yeah. But yeah, but there is a very simple reasoning. I mean, that's your reasoning will also work. But like at what Raghav has said is you focus on this part and just make ones. You have an odd number of ones on this part. If you get just like what Rasu was, that's similar to that, right? And then you just do it on this part, or you just make one maybe separate or something. Yeah, you think so, or maybe it doesn't work. Wait, so so that is why it did not work, right? Something like that. But anyways, you can work it out, right? So there'll be even number of pairs on one side and odd number of pairs on the smaller side. You can work it out like this, and you can see that you can get at least this kind of even numbers, which are 2 mod 4 for basically there's a simple solution like this. Okay, making pairs and number of ones and so on. Some simple thing. They will depend 2 mod 4, 3 mod 4, but you can do it. That is what I was looking for. Okay, so you see how bad we are. I mean, not just you, all of us. I mean, if this was asked to me directly in the class, then I would also get stuck or even trying. We are very bad at non-standard questions. If something comes which someone just made up, right? If in CMI, especially if this happens, if they just make up the question on, while drinking tea, they just make it up, then you guys will get stuck. Okay. And if they copy it from some even difficult Olympiad and there's a standard strategy, then you guys can maybe find a way. So this is what you have to change. This is because, and you see, there's what you have to do is you have to try a lot of examples. Okay. Don't think about theorems too much, but try a lot of simple things like this. Okay. This, the kids do it very well, I've seen, because they don't know much. Okay. And so anyways, I mean, we all do, but it's okay. The exam situation is a little different than, yeah. So the point of all this is the non-standard questions. Okay, so that's the merit of writing these mock tests that I'm making. That's the difference between this and other mock tests. Okay, obviously this is very inconsistent and yeah, too non-standard sometimes, but yeah. Oh, okay, sorry. So this is a new lab. This is a different machine. So I pressed the wrong button. Fortunately, it did not shut down. One. Okay, so now let's go to the next question. So the next question is not mine. The next question, I have copied it actually from somewhere. Let's try it. I think that's the only question that is copied. Yeah, more or less. Okay, let's try this one. So this is problem number 7. So let A be a, okay, 1 minute. So yeah, that question that we discussed, that can be very interesting. There's a lot of interesting variations and one can write some elementary papers based on that. Okay, like high school level research. Some other special kind of sets I can give think after some thought. And then if you guys maybe after the exam try it, right? Then it will, so yeah, like there'll be crafty solutions which will be not known but easy, but not known, not advanced but tricky, something like that, right? So with some special, but the sets have to be thought of nicely. Someone has to think of the sets nicely and predict that there will be a creative solution, and then that will be good. I'll think of them. Like instead of consecutive numbers from 1 to this thing, we can pick some special sets and try. Anyways, so I'll think about that surely. And there are other similar questions are there in my mind. I will tell you guys later. But now, so A is a matrix with square entries. Okay. So A is a square entries, means integer entries with integer entries. Okay. Show that there exist matrices B and C so that all rows and column sums are non-negative. Okay. So show that there exist P and C such that BAC. So I'm not saying it will have all positive entries, but positive sums, okay, are non-negative at least. Yeah. Non-negative. Yeah, non-negative is what we can say, not positive. Have non-negative row and column sums. Yeah, both have to be said. So this is not some matrix theory question, okay? I mean, let's see, because this is also, topic is also a sort of invariance principle, if I remember. But I don't know, let's try this. So initially the sum could be negative. Yeah, some row, sum could be negative, and you have to somehow multiply with things on left. These are matrices, so B and C are matrices, right? You tell me. I mean, you have to multiply them, right? Otherwise, how does it make sense? Now you multiply them, and you don't have to multiply. You have, no, but finally you need a matrix, right? To say, yeah. Anyways, so this matrix BAC, the row and pop, so column sums have to be. So you don't have to find the B and C. Okay. explicitly. In terms of the A, you don't have to explicitly define them. Doesn't make sense. But somehow you have to, let's just take an example, right? That will be better. So you can start with, yes. Yeah. If the row entries of B and the column entries of A, you mean the corresponding, but that is difficult to arrange, right? Because yeah, so let's try that. So let me draw one example, then you can try to come up with such a row. So let's say -1, -2, 4, 1, 4, 0, just anything. Okay. So then how would you, as 1, 1? Yeah, you mean you're trying to make the B. So okay. So you're saying mine. So you're trying to, okay. Then you take a positive value. You mean in here? Okay, 6. Oh, sorry. Okay. This is going like this. Okay, okay. But you're trying to go for something harder. So what you're trying to do is you're trying to make every entry positive. That's a very ambitious goal, but it may not be possible. I think that may not be possible. To make, you see what you're trying to do, right? You're trying to make every entry positive. I'm not asking for that. I'm just asking that the final matrix, every row ka total sum should be positive. Okay, like you take a row and you add the number, you add the elements of the row, add the ends, sorry, add the entries of the row, and that should be a positive number. Okay, like in this situation, the first 2 rows are already done. Only last row you have to make some positive. Okay, but still, this is something that you can think. Let's think. Since now the question is more clear, huh? Yes, that's right. We have to relate. So anyways, we can keep this for the first, this thing, and the first entry becomes positive. Does the second entry also become you see, then that's where it gets stuck, right? The second entry becomes negative, can become negative. Okay, it becomes positive in this case, but then yeah, you understand, right? I could have taken this to be -15. Yeah, then the second entry becomes very negative. Okay, so this like trying to make everything positive is having a negative effect next time. So don't try to make everything positive. That does not seem to be the right thing. And I will just note that and think for myself later on. I'll surely do it. These are the things, interesting things. Can every entry be made positive? I'm quite sure that is no. So just think, because now the question, you have just become comfortable with the question now. So just think sometime. Think on the spot. That is the main thing. You have to think on spot. Or every entry non-negative. Same thing. Yeah, so it's not necessary, but let's assume everything is square now. Okay, but in general, what can happen is, so in general, Oh, sorry. Yeah. So you're saying in that way. So I should have said that. Yeah, yeah. Let me check. Then there's nothing to do, but all are not zero. Yeah. So what you could do is you're saying I can pick B to be zero, right? And then the problem becomes trivial. So the problem is incomplete a little bit in that way. 1 minute. So yeah, so the problem is incomplete. Yeah. So the row sums and column sums are non-negative. 1 second. Uh, uh-huh. No, no, A inverse may not exist. That's the problem. Yeah. So first, okay. So first, to address Rasugru's question, you take everything. Just take everything to be square. Okay. Otherwise, if I don't know what happens. Yeah. Let's just take everything to be square. Otherwise, also I believe, yeah, it can be done. Otherwise, also it can be done. Okay. But let's take everything to be square. Number one. And number two is have non-negative row sums and column sums, and uh, but uh, but all entries shouldn't be zero. Okay. You don't want to make all entries zero later on in the end. So think about this too. Think about now. I'll just think one more thing I'm thinking. Right. If it is not specified square, then it is trivial. So why is it trivial? Hmm. 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 And you want a positive number. So how do right. How do you make that? But let's say how do you make that? So okay, then let's think about this one by one case. Okay, let's think about this one. No, not one by one by three and three by one, because this is simple, but I can make another question out of this. So you can first try this. So figure out some three things. And you see, once you do this version, then the square version also becomes under your control, right? The square version, because if you try to think about matrix multiplication as a linear combination of rows, and let's first do this. And let me just think, there's one thing which Chandan was trying, making all entries positive or non-negative, and at least one positive. I'm just thinking that. Make one second. Positive entry. There is a positive entry. Just this one minute. Right. Okay, right. And then after that, you can surely you can do you can make the column, right? I agree with you. That's fine. I agree with you. But you see, basically, what you have to do is, you see, if you put a in general, I'm trying to say, so you can think of it in a more um, clean way. So if you say A, B, and C, then what are you doing? Yeah, you are you are multiplying the first row by A. You're multiplying the second row by B. And you're multiplying the third row by C. You see, this is how you should think, right? Of matrix, especially when row sums are given. Yeah. This is what it is. Yeah, you're taking the linear combination of the rows. I mean, this will be the first row in the output. Okay, so and there's only one row. So forget about this thing now. Yeah. The first row of the output is given by the given by a linear combination of the rows of the matrix, middle matrix, and the weights, the combination, those scalars are coming from the entries in the first row of the left matrix. Yeah. And then you want to make this positive. And that's very simple, right? If you see any row with a negative sum, this is a positive sum, so you put a positive number. If you see a positive sum, then you put a positive number. If you see a negative sum, you put a negative number. Then surely your sum will become positive. Yeah, I mean, you can take C to be 0. Is that what you're saying? No, but I cannot take it to be any constant, right? You see, in this case, it works out. But in general, I'm saying, right? In general, if this sum turns out to be positive, then you multiply it with any positive, just multiply it with 1. If it turns out to be positive, multiply it with 1. If it turns out to be negative, then you multiply it with -1. You see? Do you guys see this? Yeah. So then negative sum will have a positive effect, and positive sum already had positive. And I mean, if the sums was 0, then I cannot do anything, right? Then the sum will remain 0 no matter what combination I take. Be careful. Yeah, the sum will remain 0 no matter what no, so that's not correct. Yeah, so you can always make the sums, you can always, yeah, so you can see, right? You can make the sum positive because, I mean, if at least one row has non-zero sum, sorry. So if all the rows have zero sum, then the row sum will remain 0 after you do it. Do you guys agree with that? Yes. Yeah. If the row sum was 0, right? So if R1, R plus R2 plus R3, if this was 0, then no matter what combination you take, it's not very magical that it will still remain 0. Oh, wait, am I getting it? Sorry. Yeah, right. So that's no, I'm getting distracted. No. That is not correct. Sorry. Yeah, that is not correct. No. So 1 minute. Oh, that is correct, right? Oh, that is correct. Why is that not correct? It is correct. Yeah. If the sum of, so basically row 1, right? Sum is 0. It means that this is sum, I mean, this is A11 plus A12 plus A13. It is 0. So what you multiply with doesn't matter. And similarly, right? So if the row sums is very interesting, but it's true, right? If the row sums was 0, then it remains 0. No matter what combination you take. No. I mean that if the row sum of R1 is 0. Yeah. So I'm saying that if this was 0, and if this was 0, sum, yeah, individually, then you cannot make it non-zero, right? Okay. If they're individually 0. Okay, I mean, you see, right? If they were individually 0, then you cannot make the row sum non-zero after taking any combination. And if one of them is non-zero, then you can make it positive. And now its problem is done. Right side, you can think of similarly. Now you can think. So you see this idea of ours, which we had developed at one point, and this problem is not that I made it just to meet that idea, right? And I don't know, they did do it by some other way in the solution. I've not really seen carefully. And I don't even know where I took it from sometime back. That's the point. Okay. This is the cool thing, that this method that we have discussed earlier, this kind of helps here. Okay, and you can see this. So once you do it with this thing, then if then if a 3 by 3 matrix, you can do it like that, right? You can think, right? So this will give you the first, this will solve the first row, right? The first row sum you will make positive. And similarly, you can get the second row and make the second row. I mean, you can just take the same thing, right? You can just take the same thing. Yeah. So you can see that. Okay. So it's a good concept. Maybe other question. Yes, yes, yes. Two of the rows positive. You mean every entry or the row sum? Every entry. Okay. How do you do that? How do you do that? Okay. So in this case, you're doing some row operations. No, so let me tell you. So yeah, in this case, if you take, so let's do this one, what you're saying first. R1 plus 2 R2. So if you do R1 plus 2 R2, then yeah, in this case, no, you don't need to do 2 R2, but this you're replacing R1 by. You're replacing R1 by this, or you can just do R1 plus R2, so you can remove this. But the point is that, see, this is little ad hoc, right? Because you do not really know in general how you will make this work. You see, right? I mean, if there's a more tricky combination of negatives, then or can it always maybe be made to work? So the question really is, if you have a, I mean, you can a 1 2 and 1 3. This is an interesting thing. 2 1 2 2 and 2 3. Then can you do some row operations? Meaning you have to only do row operation, means multiplying on the left by some matrices. We know what matrices. And if you do that, then can you make every entry positive? And so the question really is, no, but that's a little complicated to say algebraically. Yeah, so can we make, yeah, so let's think, yeah, can we make every entry positive by some row operation? In general, can you do it? So can we make, so can you, the question is, so forget the third row. There is a third row, but you don't have to worry about it. Which basically, yeah. But the question is that, can you make every entry positive? So Chandan, do you think it can be done in general? Sometimes certainly. So can anybody give an example where it cannot be done? So just, so if you have if there is an example, there's some plus minus one matrix will give an example, or something similar to that. Right. Right. No, so the reason why I am thinking it may not be possible, or is it possible? I should know. That we have already proved, right? If you are saying that, is that right? That we have already proved. The column row sum can be made positive is kind of now easy. We have already said that. You just take the right combinations to make the first row positive. Just say take the same combination and get the second row. Just take it to be the same. I mean, so B will have equal rows and everything. But that is not the point. The point is you want to make every entry positive. Just a minute. So it 1 minute. It can be done. You can. One minute. So just using row operations, can you make at least 2 rows if there are? Can you make them positive? So I'm just thinking of row operations from linear equations perspective. So finally, how simple can you make the final matrix? Okay, you can make it like this, and then you say that there is another variable. So how do we say that? So if we say there is an entry like -2, then we say that you can take to be that. If we say that it is 0, no, I don't think that is correct. Yeah, you cannot make every entry positive. But let's not get into the reasons of that. Okay. You can try to think if you want. And if you think, then you can ask. I will surely try. I'll surely help. Try to help. But that's not a part of the main. That can be a complicated question. Just give me 1 minute. 0. If it is non-zero, then what does it mean? So it means that y minus 2z is something. And that means you can put z to be, yeah. So no, I don't think, yeah, that's not, may not be possible. Seems unlikely. Okay. Seems unlikely. Yeah. But then let me then say this thing. This is a small question. Since people seem to be interested in a little bit about all entries can be made positive or not. Okay. Let me just ask this question. This is simple. So if A is this, okay. Now, if for all row vector V and column vector W, okay, for all this thing, VAW is positive, okay, then show that every entry of A is positive. It's a very simple question. Okay. All right. So you can think of this. So maybe you can think of this as well. Show that every entry of A is positive and every entry of P inverse AP and the square matrices is positive for all P. Okay, so that's a little more. And now there's a question for me. Is BAC positive? Is every entry of BAC positive? Entry of BAC positive for all B and C. This I will think. Yeah. This also the answer should be no, but I'm not giving this for you to think now. You can think, but these two first you said. Okay. All right. So that's what it is. So if there are any questions, if there are no questions, then let's do the last problem. Okay. Okay. So let's do the last problem. Yeah. So this is a kind of a game on a graph. So this is the 8th problem. Okay. So this is a huge question. So it looks huge. So a directed graph on N has to be transferred from Tom to Jerry. Okay, so there's a directed graph with Tom. Okay, some map of something or something, and it has to be transferred, and has to be transferred through this person Alina. And so Tom tells the graph to Alina, and by mistake, Alina reverses all the edges incident to a particular vertex. Okay, and no other error is made. And Alina then tells Jerry this graph and the vertex where the error was made. But but what Jerry can do, so this is strange, but by doing the same at some other subset of vertices, recover back the original graph. That is the first question. Okay, not at the vertex where the change was made, but some other vertices. Let me say it through a example. So it's like a reorientation of these things. Yeah, I could have made this question much more cleaner. So, but anyways, so even if you don't know which vertex the error was made, if you make the switches randomly, you should get back the original graph. Let's not think. I'm not able to think now too well. Anyways, let's do this one. So let's say the thing is that let's say you have like this. Yeah. Okay, so you can see there are some cycles, but there is no directed cycle. Yeah, this is not a directed cycle because the arrows don't go in the right way. So let's say this was the original graph, and now the new graph that has been given is the following. Yeah, the change has been made here. So let's say that vertex is not accessible for some reason, then one can frame it like that, where the error was made or it was lost or something. Yeah, and then things got reversed like this. Yeah. Now the question is, can I do the same thing at the other vertices and get back the original graph? Right? Or at some subset of vertices. Can I do the same thing at some other vertices subset? You're allowed to do that at many vertices. Okay. So can I do the same? So is it understand what I mean when I do say, can I do the same? So you're allowed to pick some other vertex, use some other vertex only once. You can use many vertices, but you cannot use one vertex again and again. And probably that's not very useful also. But anyways, probably it could be put in general, and so you will end up using it many times. But there'll be a solution without using it many times. Can I do the same at other vertices? And get back the original graph. So in this case, the answer is yes. Okay. And this actually answers some very fundamental question in something in algebra. Okay. Yeah. Some very interesting, and that's how this question somehow just popped into my head. It was not obviously the question. It's not like this. If something, but there is a analog. This is an analog of that. No, so it is not lost, but let's say that you're not allowed to do anything at that vertex anymore. You're right, and that's what the question is saying. So can I do the same at other vertices? Okay, so you're not allowed to touch that vertex anymore. Let's say I've just put it like this. Say you can put it in a more creative way, but oh, oh, sorry. So that's wrong. So that's incorrect because I just yeah. So this is just that is just a typo. So, yeah. Okay. So can we get back the original graph by doing the same thing at other vertices? So you can imagine, like, if you do it at the other vertices, then what do you get? You can just try, take small case and see. Maybe take a smaller case and see. And then you have to change the adjacent of adjacent. Something. Okay. So let's see if we make the change at 3, then what do you get? So then some things get fixed and some things get worse, kind of, maybe. Right. So let me first label the vertices. What is happening? This is 6 and this is 5 and this is 4. So you see, if you're doing it at 3, so the change is being made at 3. This change has a name, but then this becomes like this. So let's first change everything at 3. So you change everything at 3, you make it like this, right? And other things are remaining the same. So the graph is not exactly what we want. So now you can say you have to make the change at 5, right? So, but then when you make the change at 5, then what happens? Right? You make the change at 5, then what happens? So this becomes like this, and this becomes like this. But yeah, but then the 4 gets messed up. So I'll try to make the change at 4. But then how will this thing end? In this case, just try to think, you can see a pattern. Or take a smaller graph and try. I don't know what is itching me. So Adish is not well since some time. He's having fever and such. Okay, so so in this I switched 3 as to I made the change at 3, but then I also made the change at 5 after that. So 3 and then I made the change at 5. Right? You can see, so at 5 also things have changed. But now you can think, right? Now you'll make the change at 4, and then you can make the change at 2 and make the change at 1. Right, but that's right, but really, yeah, you have to think, like, in what order do you have to make the change? Is that right? Does everybody see that? Yeah. Is it important in what order we make the change? Because then it can get really complicated, right? Is the order of the moves, right? Whatever order of the vertices or whatever moves important in the end. So now I think you guys should just think about this. Okay. Yeah. You see, in this particular case, you see some key features that we ended up making the change at every vertex. Yeah. We made the change at every vertex only once. And we got back the original graph. Is there a surprise? Right? It's not a surprise. Yeah. So you see, that's the answer to the question, right? If you make the change just, and it's a very silly question in that sense. I mean, at least the first part, yeah, that if you just make the change at every vertex, then you get back to your original graph. There should not be any question about it. No, right? The order doesn't matter, right? Because if you make the change at every vertex, then what happens? Every edge, its orientation changes twice. And so it gets set back to its original thing, right? Except for the edges which were, coming out of, or, which had, that 6 with it. And they only change once. And so that's good for them. And the other edges change twice, right? Because they are part of 2 vertices. Yeah. And then we're done. Simple. You don't it's not even important whether you have cycles or not in this case, right? It's just simple. So you make the change at every vertex and the order doesn't match. It's a very elegant solution to it, but you have to get, so that's it's good. So see it's a flip. You do it twice, and so it doesn't. Okay. Yeah, is it clear? Chandan and Rasuru, is the argument okay? Yeah, it's a very simple argument. Okay, but it's a yeah. But now the next question next part you have to think. Okay. Can you now do this by making, but now you're not allowed to make it at, no, you're not allowed to make it at every vertex. Now you have to allow to make it at sinks. Then how do you do it with just doing it at sinks? Will you be finding, will you be able to find sinks, or do you have to do it at all sinks? And, or I don't know, you have to think. So think about the part B. Okay, it's not difficult, but it's really interesting. So algebraically speaking, doing it at the sinks is useful in the algebraic sense. Okay, so then that's a different thing. So there, what happens is we put some at each vertex. We put some. Let's say you put at each vertex you put R2, R3, or R4, or something like that. R2 or R2. Let's say for you thing. And for each arrow we put a function between those 2 spaces, and then it becomes a big space and sum of spaces and functions, and then becomes a matrix theory along with it, and some other things get mixed up. And then we ask, like, truly how many different ways are there? Truly how many different ways are there to put these spaces and put these functions? Like, they are infinitely many, it seems like, but truly there are only finitely many, up to some ISO, some similarity between them. Some basic feature of many of them is the same. And so to answer that question, we need to do some kind of induction, and to jump from one place to another place, to a simpler place, we do this arrow switching. And somehow it helps us. Yeah. Anyways, that's yeah. Okay, so then that's it for today, and maybe tomorrow the other, if you get time, just try the paper. Then tomorrow we can discuss that paper. And if you don't do it, then we can discuss something else. Okay, I will continue with the topics that we had. A little bit of asymptotes was left. One on differential equations was left. Parametric equations I had planned, because I skipped all the classes. So we can discuss that. So, but yeah, let's see. Okay, I am okay with both. Yeah, and the new mock test also, I think I have written 2-3 questions. I just add 1 or 2 more questions when they come to my mind somehow in something, then it will be interesting. Okay.